Take a look at questions 4 and 5 on our homework last night, worksheet number 12. Starting with question 4. It says, what's the kinetic energy in joules and electron volts of an alpha particle that moves through a magnetic field strength of 0.1 Tesla, follows a circular path of radius 0.025 meters? Let's circle a couple things here. First of all, we're looking for the kinetic energy in two different units, joules and electron volts. So joules is the standard unit. That's what we're probably going to find first, but then we got to remember to convert that to electron volts. The second thing I want to draw attention to is the fact that we have an alpha particle. Remember that that's a positive particle, and if you're going to have to use a hand rule, it's going to be a right-hand rule. Okay? Doesn't look like in this question we're going to have to use a hand rule, but in the end we still want to remember that it's not an electron. You think like, well, why would I call it an electron? It says an alpha particle because it's habit, right? We use electrons so often it becomes habit that we make the charge 1.6. All right, so what do we got here? We want to find the kinetic energy of an alpha particle. Well, the only way we can find kinetic energy is to say Ek is equal to 1/2 mv squared. The only problem is we don't know what the speed is. So let's find v. What else we got going on here? A charged particle is going through a magnetic field, and it follows a circular path. So as we learned yesterday, the centripetal force is equal to the magnetic force, right? Charged particle goes through a magnetic field, follows a circular path. Set those two forces equal to each other. mv squared over r equals qvb. One of the v's cancels. We're looking for the value of v here. Becomes r goes up by multiplying q times b times r, and then m goes down by dividing. So we've got 3.2 times 10 to the minus 19, the charge of the alpha particle, times 0.1 Tesla times r, 0.025 meters, divided by the mass, which is 6.65 times 10 to the minus 27 kilograms. What are we end up getting for speed there? Nick, you get the value of speed there? Ten to the 37? Okay, that's where you made a mistake then, is on the speed, because we know that the speed isn't going to be greater than 3 times 10 to the 8 meters per second. That's the speed of light, and nothing's going to be faster than that. Okay, accelerations can be whatever, and sometimes we get mixed up. Like, oh, we got a giant acceleration, we can't have that. Well, yes, you can for acceleration, but not for speed. So let's go through that on the calculator then to see how we get the right value there. We're going to say 3.2 times 10 to the minus 19 times 0.1 Tesla times 0.025 for the radius. So let's divide that by the mass, 6.65 times 10 to the minus 27. And I get 120,300. 120,300 meters per second. That seems more reasonable, right? We're talking 1.2 times 10 to the 5 meters per second, which now we're going to plug that in here and solve for the kinetic energy. And what did it work out to be? I think 4.8 times 10 to the minus 17, I think it was. How do you convert that to electron volts? 1 electron volt is 1.6 times 10 to the minus 19 joules. X electron volts is 4.8 times 10 to the minus 17 joules. Okay, the 4.8 goes up by multiplying, and then we divide the two, it works out to be 300 electron volts. Good? Okay, 5. Boy, 5 is an ugly one. I think 5 is an ugly one anyways. It's phrased actually with a slight error in it, but probably nobody caught that. Just how does the radius of curvature of an electron compare to the radius of curvature of an alpha particle? What it should say is, how does the radius of curvature of an electron's path compare to the radius of curvature of an alpha particle's path? Because we're not talking about the radius of an electron compared to the radius of the alpha particle. We're talking about the radius of the path of the electron compared to the path of the alpha particle. Let's do a little analogy here to guide you as to where we're going to go with this. Okay, I want to compare two things. I want to compare here the radius of an electron's path to the radius of an alpha particle's path. Let's compare two other things. Let's compare my age to your age. How old are you? How old are you guys? 18? Most of you guys are 17 or 18. Okay, let's say you're 18. Okay, that works well. Okay, let's say, even though not all of you are quite 18. Okay, let's say that I'm 36, even though I might not be quite 36. Compare my age to your age. Compare the teacher's age to the student's age. Anybody. Remember, you're 18, I'm 36. Compare my age to your age. I'm twice as old as you, right? Okay, if I'm 36, you're 18, I'm twice as old as you. You figure that out by dividing the two values, 36 divided by 18. Whenever you want to compare two things, to numerically compare two things, that is, like we're not talking about, oh, let's compare the color of this to the color of that, right? But when we want to numerically compare two things, then we're going to divide the two numbers. You want to compare two ages, divide the two ages. You want to compare two radiuses, divide the two radiuses. So here's what it's going to be. We're going to say the radius of the electron's path divided by the radius of the alpha particle's path. Just like it was the age of me to the divided by the age of you. Remember that. Whenever you want to compare two numbers, you always think divide. Compare equals divide. All right, if we have the radius of the electron's path and the radius of the alpha particle's path, it's an easy question, just like comparing my age to your age, right? We got the numbers, just divide them, easy. Problem is we don't. We don't know what the numbers are. Okay, if we don't know what my age is and your age is, it becomes more difficult to divide our ages as well. So what do? Instead of dividing a number for Re and R alpha, let's divide an expression. Now we can derive an expression. We know that Fc equals Fm. Centripetal force equals magnetic force. mv squared over r equals qvb. And I can cancel out one of the v's. Solve for r. The r goes up by multiplying. The qb goes down by dividing. And I end up with mv over qb. So what I want to do here is sub in. Here, let's change this a little bit here. Let's sub in mv over qb for the radius of the electron's path. And then let's divide it by mv over qb for the radius of the alpha particle's path. So what's in blue there is for the electron. What's in black there is for the alpha particle. You could put subscripts beside it as well, right? ME, VE, QE, BE, M alpha, V alpha, Q alpha, B alpha. There we go. Boy, that's an ugly looking equation. We know the mass of the alpha particle and the mass of the electron. Oh, wait, the speed is the same, right? Look, the speed of the electron is the same as the speed of the alpha particle. So even though it's two different variables, it's the same value, they can cancel. Magnetic field strength is the same as well. Okay, that simplifies things a bit. Now we've got an equation that says mass of the electron over the charge of the electron divided by the mass of the alpha particle divided by the charge of the alpha particle. Hey, we know all those numbers. So now we can do this. We can simplify it a little bit if we want, but we don't have to. We could say that's the same thing as saying mass of the electron over charge of the electron times charge of the alpha over mass of the alpha, because right, we multiply by the reciprocal. Now, we know all these numbers now, right? 9.11 times 10 to the minus 31 divided by the charge of the alpha particle, which is 3.2 times 10 to the minus 19 times, wait a sec, what do we got here? This should be the electron, right? So we do the math there. get 2.7 times 10 to the minus 4. So if the ratio of my age to your age was 2 to 1, then the ratio of the electron's path to the alpha particle's path would be 2.7 times 10 to the minus 4 to 1. It's a kind of an odder number than 2 is, but it doesn't usually work out to be such a nice even number as 2 to 1. That's why I said my age was 36 instead of what it really is. Yep. No, it's just a ratio, so there's no units. Just like there's no units for the ratio of my age to your age, right? I'm 36 years old, we'll say, but the ratio is still 2 to 1. We wouldn't say 2 years to 1 year. It's just 2 to 1. Good. All right, your other bit of homework that you had last night was some questions from your textbook, page 601, number 3 to 6A, and 7 to 10. All right, let's have a look at page 601, number 3 and number 5. Question 3 says, an electron and a proton, both with the same perpendicular velocity, enter a region with a uniform magnetic field. What can you state about the deflections of both particles? All right, that's a good question. Okay, so they're asking us to state something about the deflection of both particles. Odds are they have something in common. Odds are there's something different about them. What do you think they have in common? The deflection of an electron and a proton, same velocity, same magnetic field. What would they have in common? What would be the same about them? Yeah, Jacob? They both have charge, yeah? But what would be the same about the effect on them? What happens to them? Okay? Yeah, the magnitude of the magnetic force would be the same. QVB. Q is the same, V is the same, B is the same. The strength of the force would be the same. So what's different about them? If the magnitude of the magnetic force is the same, what's going to be different? Q? The direction of the magnetic force. One's a positive particle, one's a negative particle. One would be the left-hand rule, one would be the right-hand rule. And we'd have opposite direction. Good? All right, and number 5. A positively charged lithium ion is traveling horizontally along the Earth's surface. Describe the deflection due to the magnetic force if the ion travels south to north, east to west, upward into the atmosphere. When we say south to north, we're going to assume geographic north here. Okay, we're going to assume that we're talking about the Arctic, right? So let's say, look, the magnetic field is going from, the particle is going from south to north. That's the North Pole, right, or geographic North Pole up there towards Calgary, towards the Arctic. The particle is going that way as well. What do we know about the magnetic force if the particle is going that way and the magnetic field is going that way as well? Yep, it's 0. The magnetic force is 0 in that case. What about if it's going east to west? Well, that's west. You see the mountains out there, that's west. The magnetic field is still going that way. I've got a positively charged ion that's going towards the west, so right thumb towards the west. Fingers get stretched out in the direction of the magnetic field, which is toward magnetic south pole, which is towards Calgary. Palm points downwards. We're not going to say down the page here. We're going to say down because our frame of reference is the Earth. So it's down towards the Earth. And upward into the atmosphere. Okay, thumb upward into the atmosphere. Fingers still point towards magnetic south, like this, towards Calgary. Palm points towards the, don't say towards the right. Which way are you going to say? A frame of reference is the Earth, north, south, east, west, all throughout this question. So which way is my palm pointing? Yeah. Yeah, towards the west. Yeah. Good. I want to spend a couple of minutes going over one more practical application of what we've been talking about, and then we'll go on and do a little bit of new material here today, okay? This is what we call a cyclotron. A cyclotron can be used to collide particles, Nick. To collide particles. Why would we want to collide particles together, subatomic particles together? Because we want to find out sometimes what's inside them. Sometimes the best way to see what's inside something is to break it open. Okay, I remember when I was in grade 10 biology. I still remember this. It was we wouldn't do this now, but back then it was they did it every year. It is what it is, right? In grade 10 biology, I remember we dissected, or we took eggs, growing eggs, like chicken eggs, at various stages of development, and opened them to see these chicken fetuses inside. And sometimes they were alive. Sometimes they were these, I think the cycle is 21 days, and sometimes, I forget at what point they could still survive, but sometimes they looked hardly like a chicken at all. And it was kind of a game to see how long we could keep them alive for. It was cruel. It was terrible that we did that. But that's the way it was back then. But my point is of that story is we wanted to see what's inside these eggs. So what do? We break the eggs open, right? You want to see what's inside of something, you break it open. Okay, you want to see what's inside of these subatomic particles. Sometimes you speed them up to really, really high speeds, and then you crash them into each other and you break them open. Okay, it's sometimes brute force is the best way to see what's inside of something. So here's what happens in a cyclotron. You accelerate these charged particles, okay, and you accelerate them by constantly going across an electric field. Here's the electric field region in here, right in here. Okay, charged particles accelerate across an electric field. Remember, as they go across the electric field, you have a conversion of electric potential energy to kinetic energy. It's like a car going down a hill, but it's not enough to go across a potential difference once. It speeds it up, but it doesn't speed it up to a high enough speed to make the collision worthwhile. It's kind of like saying, here's an egg, we want to find out what's inside it. Let's drop it from a height of 2 millimeters and see if we can break it open. It just won't break open. We have to drop it from a bigger height. We have to give it more energy. We want to collide these subatomic particles together and see what's inside. We have to give them more energy. We have to make them go faster. So we have to accelerate them across the potential difference many, 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 many times. So how do we do that without having a million different potential differences? Well, it's kind of ingenious here the way that it's done. You inject an ion or whatever subatomic particle it is that whatever charged particle it is that you're trying to examine here. We inject these charged particles right here, right smack in the middle, and they accelerate a little bit across this gap. And then they're going in a circle. And then they accelerate more across the gap. And then they go in a circle. Well, not quite a circle, because the radius keeps getting bigger. Why does the radius keep getting bigger? Why do you think the radius of the path would keep getting bigger, Nick? Yeah, because every time they go across the gap, they have more speed. So it goes in a circle, a semicircle, speeds up, goes in a slightly bigger semicircle, speeds up, goes in a slightly bigger semicircle, speeds up, and so on. So every time it goes across the gap, we've got a conservation of energy problem where we say EI equals EF. But how do we get it going in the circle, constantly going across the gap? We introduce a magnetic field. And a magnetic field has to direct these charged particles to go in a circle of particular radius. So my question for you here with this, with the setup that we have, is what's the direction of the magnetic field? If we have positive ions, which direction does the magnetic field have to point? Well, the first thing I want to do is draw attention to the fact that it's positive ions. I'm going to use my right hand for this. It's going to be the right-hand rule for deflection. What a lot of people do when they see something like this is say, oh, it's got to be the coil rule, because it's kind of like coiled up. Guys, that's the magnetic field that's kind of coiled up. It's not a wire that's coiled up. It's not the coil rule. It's simply going to be the hand rule for deflection. Charged particle is deflected in a magnetic field. So how do we find out the direction of the magnetic field? What we want to do is pick a single spot for a particle. Doesn't matter where. Let's pick right here. At this point, the particle is going upwards. Thumb in the direction of the particle going upwards. We don't know which way the field is. Which way is my force? We all know this. Which way is the force? Okay, we talked about this yesterday, right? Charged particles going in a circle, the force is always directed where? To the center of the circle. So at this point, the force is to the left, right? Thumb, force to the left, fingers point into the page. The magnetic field, in this case, would have to be into the page. That make sense? What if we had to pick a different spot? What if we had to pick this spot to examine the moving charge? Well, it would be moving in this direction at that spot. We'd stick our thumb in that direction, palm points toward the center, my fingers would still automatically point into the page. So, hey, this would be a great question for an exam. Got a cyclotron, don't know anything about cyclotrons, right? I mean, you do because I've taught you here today, but there's lots of people in the province that wouldn't. This is just an application. It's not a curriculum objective. So how are they supposed to answer the question? Think about what they know. Right? What do we know? Charged particles get deflected toward the center of the circle. They're moving at any given point tangential to the circle here. So it's a thumb, palm, fingers go into the page. You're going to see something like this on an exam? Probably not. Are you going to see some other application that's different than this one? Yeah, probably. Yeah. It would probably be, the best question that I can think of would be, which way is the magnetic field? Or if you were given that the magnetic field is into the page, tell me whether it's a positive ion or a negative ion. Okay. Make sense? Now, I could also, going back to our last unit, we could also ask you for, okay, let's say it enters right here at a speed of, at this point, it has a speed of, let's say, 2 times 10 to the 4 meters per second. And it goes across the gap, the potential difference, big V, of, I don't know, 2,000 volts. What's the speed as it gets to the other side of the gap? In that case, it would be, right, QV plus 1/2 MV squared equals 1/2 MVF squared. So you could be asked something like that as well in that question. That's not what I wanted to, the point that I wanted to make today, but certainly that concept is applicable there too. But you'd have to be given some data there for it, obviously. All right. Here, let's do a couple multiple choice questions here. First one that I'd like you to look at is multiple choice number 75, and you might as well do 76 along with it since the two of them go together. Time to have a look here. The question says solar wind consists of particles emitted by the sun. Some of the particles are charged, therefore, when they enter the Earth's magnetic field, they experience a magnetic force. We talked about a little bit one day earlier in the unit about the magnitude of the Earth's magnetic field decreasing and potentially reversing, and some of the implications if the magnetic field actually becomes zero at some point. And one of the implications we said is solar wind particles, positive particles coming from the sun that get deflected by the Earth's magnetic field. Well, what happens if the magnetic field is zero? Well, they no longer get deflected by the Earth's magnetic field. So some of them get absorbed by the Earth's atmosphere. It's not like they all just hit the Earth and do crazy things to us, but more of them will encounter the Earth. More of them will hit the Earth because they're not deflected by the magnetic field. We've got these charged particles at 8 times 10 to the 5 meters per second hitting magnetic field strength, a weak magnetic field strength of 1.1 times 10 to the minus 7. And we're told that somewhere down here, I think we're told that they're protons. Oh, is it in the question? Okay. So we don't see that anywhere here. Guys, look, we got charged particles going perpendicular to the Earth's magnetic field. They're going this way. The magnetic field is this way. They're going to experience a force, right? And we can find the force, the direction of the force, using the hand rule for deflection. Notice the diagram of the Earth here. They have a little bar magnet drawn inside with a south pole at the top. Okay, magnetic south in Canada. All right, let's see what we got here. Protons in the solar wind means right-hand rule. Experience a magnetic force which way? We're going to say right thumb in the direction of the particle, fingers in the direction of the magnetic field, which at that point is toward the top of the page, palm points out of the page. So for you guys, it's still going to be out of the page, but your hand's going to be like this, right? Because your page is horizontal. So the answer for that question would be out of the plane of the page. 76, assume that the velocity of the solar wind particles is perpendicular to the magnetic field. What's the radius of the path? This is just going to be a FC equals FM. MV squared over R equals QVB. And we're looking for, what are we looking for? R. So V cancels, R goes up, QB goes down, R becomes MV over QB. What did that work out to be? 7.59 times 10 to the 4 meters. Thank you. Anybody agree with that? So we'd express that as 7, 5, 9, 4. Good?